Hi, Jerry. Hi, Xun. Hi,
Hello.
hi, Xun. I'm going to host our seminar today. And it's Shikai here, this discussant. Yeah, Jerry, please find Shikai. Xun, would you be able to share the screen? Let's see how that works.
Of course. Yeah. I think the host needs to enable screen sharing. Oh, yes. Thank you. Let's see. And let me try full screen. Does that look okay? Is it full screen?
Looks great.
Oh, excellent.
Okay. So, Xun, how long do you plan to speak about the talk?
I think I have 35 slides on my estimates, maybe 45 minutes. Does that sound reasonable? Or
Yeah, it's totally okay. I just don't know how long Shikai plan to discuss. Have you two talked before about?
Yeah, I sent him some material, like the slides and the papers, but we haven't discussed the main, like, detailed what we want to talk about. So I'm not too sure.
Oh, no problem. So let's just make it parallel and interactive. So
Sounds
I think
great.
it's the right time. So maybe I can start to introduce you. Welcome to our ARL seminar today. We're glad to have a professor. Oh, I'm sorry, I did not find your introduction on the web. So hold on a sec.
No problem.
All right, let's totally cut this off before we post online. Let's find Professor Hans. Sorry. Can you please? Yeah, it's not in our website yet, right? We haven't upgraded our website. We can use this time to wait for more people to join, so it's okay.
Sounds great.
It has Professor Huan's present intro, but there's no Shikai's intro. Do you have that as well? Did you send that? Okay, great. So yeah, let me get started. So let me start by introducing. I'm going to move your. Okay. Professor Huan is an assistant professor of mechanical engineering at the University of Michigan, where he leads the uncertainty quantification and the scientific machine learning group, and is affiliated with the Michigan Institute for Computational Discovery and Engineering, Michigan Institute for Data Science, Precision Health, and Applied Physics. Dr. Huan received a PhD in computational science and engineering from MIT, and was a postdoc researcher at MIT and the Sandia National Lab. His research interests involve methods for optimal experimental design, Bayesian analysis, inverse reinforcement learning, and physics-aware data-driven modeling. So we will talk about his work on Bayesian sequential optimal experiment design for nonlinear system via policy gradient. After this talk, we have a discussion today. Dr. Shikai Luo, who graduated from Wanggang University in 2011, got a bachelor degree. Then in 2016, he got a PhD degree from North Carolina State University. His research focused on causal inference and reinforcement learning. published many papers in top-tier statistical journals and top-tier machine learning conference. He was a quantitative researcher at Quant Lab, and also a scientist at DD, Tencent, right now at ByteDance. Without further ado, let's welcome Professor Huan.
Great.
Get started, Xun?
Yeah. Sure, I will do that. Thank you so much, Ray, for a great introduction. Thank you, Ray. Thank you, Jared. Thank you, everybody who are organizing and having me here. It is definitely a privilege, and thank you, everybody, for being here today. Good morning, good evening, wherever you are. My name is Xun Huan. I am very excited to talk about some of our recent work on Bayesian sequential optimal experimental design for nonlinear system, nonlinear models with the use of policy gradient. And this work is spearheaded by my PhD student, Wanggang Shen, and he has absolutely done a wonderful job. So please give all the credit to him there. Let's see, next slide. Okay, perfect. So our use of reinforcement learning is in the applications of designing experiments. And the experiments are everywhere around us, and in particularly from residing in a mechanical engineering department, I have seen various kinds of experiments and even had the opportunity to play with some of those. So experiments could be taking the place inside a laboratory, like a physical experiment on batteries here. It could involve human subjects, right? Putting sensors on humans to do different activities. It could be related to deploying sensors into the field, collecting maybe pressure, moisture, temperature measurements that are needed for weather prediction. They could also be digital, in the form of digital gathering user data online or data from surveys. So experiments can take the form of various forms, but for us, we're thinking them as the mechanism for us to get data. And as you can imagine, that is very important for all kinds of scientific and engineering research and for learning in general. Now, whatever these experiments may be, in general, I think we can all agree that experiments tend to be expensive. They can be very time consuming and very delicate and not easy to set up and to perform. So it's important for us to try to design good experiments and ask questions such as, what conditions should we carry out this experiment? What quantities should we try to measure? Where and when should we take these measurements, especially if there are only limited opportunities to take measurements? How many experiments do we need in order to achieve some objective that we have in mind there? So all of these questions are concerned with the field of experimental design or design of experiments. Furthermore, what the type of experimental designs that we're going to focus on today here is the so-called optimal experimental designs. And this may be in contrast to many of the classical designs of experiments that are model agnostic. So there are a lot of excellent design methods out there that do not require a model, and they're more exploratory in nature. So a lot of factorial designs, different types of space filling designs, uniform designs, Latin hypercube. So in those cases, all you need to know is about what your design space is that you need to cover. And otherwise, you do not need to know, you don't need to have a model. For optimal experimental design, we want to take advantage of a model if we have one there. And the model could be something as simple as a linear model, like on the screen here, or it could be something more complicated that describes, let's say, the physical phenomenon or the mechanisms that's happening behind the experiments. So for a linear model here, there are lots of classical linear experimental design theory out there, developed many years ago already. For instance, that if we want to we can minimize the determinant of the covariance of our estimator of the model parameter theta hat, and that actually turns out to be the inverse of the Fisher's information matrix there. So we want to focus on these type of model-based optimal experimental design in this work here, try to leverage any knowledge that we may already have in describing the phenomena of the experimental process there. Okay, the type of models that we're going to look at, again, inspired by many applications from mechanical engineering, aerospace engineering, they're going to be, or we're going to be very interested in these big, complex models. For instance, an example here is a project I worked on a couple years ago, where we have a simulation model, right, that describes the flow that enters and exits a scramjet engine. So this is an aircraft engine that's designed to fly at hypersonic speed, so Mach 5 times the speed of sound or higher, very fast. So in these extreme operating conditions, there's lots of things that we don't really understand, the different types of physics, the different type of characteristic behavior of these engines. So simulations are very, very useful. And in these cases, excuse me, and in this case, for instance, we have the animation here that illustrates the simulation results from running this model, where the flow enters and it reacts with the fuel being injected and some combustion happens inside there that provides propulsion to this entire engine there. And these simulations, these models are very advanced. They are also very expensive. So running one of these simulations under a particular setting, it took, I think, weeks to do, even when parallelized on a supercomputer. So, so that's quite expensive. But nonetheless, we still want to try to leverage these kind of simulation capabilities, these predictive capabilities to help guide the design of our experiments there. Now, one thing I also want to kind of clarify a little bit here is that these type of experiments, the measurements we get, we're going to focus on when we have indirect measurements, and the measurements are potentially are noisy, and we only have limited opportunities, so very sparse measurements here. So what I mean by that is often when we do the experiments, for example, here is a tensile test that's being carried if we want to test the property of a new component or new material that's being produced there. We can, pull this component apart and see how much force do we apply and how much elongation does it occur in order to know about its let's say elasticity properties there. So in these cases, we are interested in knowing about these material property constants like Young's modulus. Now, there is no Young's modulus ohmmeter. We cannot measure that Young's modulus directly. There's no such instrument, right? But instead, what happens is that we would need to observe on something that's related, that depends on the Young's modulus, such as the strain. So how much does it elongate there? And there are countless other examples. I take some flying lessons, and one of the things that's very important in flying is you need to know how high you are in the sky, the altitude. But there is no, nobody using a ruler to measure how high your plane is, but rather the principle behind these altimeters that tell you how high you are is based on the pressure differential, right? So we are really measuring pressure difference where you are in the sky to the ground, the difference, in order to infer or estimate the altitude you are at there. So, so all of these, you can kind of see the theme that the model plays the role that connects between the thing that we want to know about versus the thing that we can actually observe and measure. So in that sense, it's an indirect type of measurement. And I think there's some background noise there. Right, and that's why the models are very important. Now, these examples are linear relationships, and we're also interested in many complicated nonlinear models. For instance, the models that govern the flow, the fluid flow around the airfoil here, very nonlinear turbulent phenomena, and we may want to take measurements to try to know, oh, is there a defect or a kink at the leading edge here? In underground geophysical applications, the process that governs the diffusion, and maybe there's some convection underground there, and the different properties, there also can be very nonlinear there, where we're taking a measurement at some point, but we want to try to know about, let's say, the permeability property of this soil in order to, let's say, prevent or limit contamination from these factories. Okay, let's see. Great. Now, if we can do multiple experiments, that's where things can get really interesting. If one approach to design multiple experiments is just, okay, we can do, let's say, 5 experiments and just let's design all these experiments simultaneously and do them. But what that does not take into account is that the possibility of updating and adapting as you do one experiment or as you do some of these experiments. So the sequentialness is not captured if we do such a batch design or a static design there. So here's an example to illustrate that point. Let's say we have some contamination leak again, and this plume of contaminant is maybe diffusing and maybe also carried around by the wind. So there's some convection there. And we may have some initial guess of where this contamination location might be. So high probability, medium, low. So I'm more of a thinking a Bayesian manner here. So that will be our prior distribution. And then we can send a probe or a drone to take measurements and try to infer where this is. Now, if we're designing everything a priori, doing a batch design, then maybe our plan is to fly to the highest probable location and kind of just follow this plume as it's being pushed around by the wind and nothing is being updated or adapted there. In sequential design, then we want to take advantage of this opportunity for adaptation. So, so we can, in this case, fly to an initial look. Oops, let me try again. Okay, initial location, and I've tried to pause, but I think I cannot pause. But let me do that again. We fly to an initial location, update our probability belief, and based on the updated state, and then design the next experiments. So there is a sequential adaptation. And furthermore, we can use the fact that in this case, for instance, the wind is blowing towards us or in a particular direction. So maybe we can also take advantage of that and maybe intercept this plume and not spend all of our fuels at once to chase after the plume, right? So this, this notion of looking ahead, planning for the future is also can be very beneficial in sequential experiments there. Okay, so when designing sequential experiments in our work here, we really want to look for the mathematical optimality of these sequential designs here. There have been quite a lot of sequential design. The majority perhaps falls under the greedy design approach or myopic design, where you plan for the next experiment, update, and then you plan for the next experiment, so on and so forth there. So it may be lacking this element or this potential benefit of looking ahead, planning for the future. And we can really try to do that if we have a model to predict what might happen in the future. Optimal sequential design then we really want to use, let's say, these Markov decision processes, reinforcement learning type of formulations to find the optimal policies that can take into account of both the adaptation and the looking ahead properties here. But these attempts are very expensive, or these formulations are very expensive. So especially if we want to do a full Bayesian experimental design, so necessarily we need to take advantage of any simplifications or special problem structures. We have also tried to do an approximate dynamic programming and seen some success, but one takeaway is that it was very expensive. So we're trying to advance the computational feasibility as well in this work using the policy gradient type of reinforcement learning approach. Okay, so let's jump into the math. The scope of our problem is that we're going to look at a design of a finite number of experiments. So it's a finite horizon problem where the experiment index k goes from 0 to n-1 for a total of n experiments. And in this case, we're assuming that we're interested in learning about some uncertain model parameters, theta. So this is the thing that we want to learn, right? So not the thing that we can observe, as we introduced earlier. We're going to reside in the continuous random variable space there. So if we treat theta as our state, then this would be a partially observed Markov decision process, POMDP, because we cannot measure theta. We cannot measure the thing that we want. We can only measure on something that depends on theta and maybe estimate theta or infer theta. Then we can prescribe or describe our current belief or distribution, uncertainty distribution about theta right now, and introduce a belief state. So XBK is the belief state. And maybe there's also physical states that are relevant to the problem. So we can also incorporate potential physical states here. So overall, we can view this as the new state. And if we treat this xk as the state, then this becomes a Markov decision process again, MDP, but for a belief state, so a belief MDP. Then the designs, we're going to use the D for the design at the kth experiment. So it is now the output from a policy mu k that would tell us what experiment we should do based on the current state xk. And for notation, I'm going to use pi, the policy that is the collection of all the policy functions at all the experiments. Since it's finite horizon, the mu's will be different for each of the experiments. So we want to keep track and compute all of those. So pi is just the shorthand form, is the overall policy that we have there. The experimental observations are YK, denoted by YK, and there's going to be a system dynamics or the state transition from one experiment to the next, according to this curly F. So what that would be for the belief state, as I kind of hinted earlier, I'm going to take a Bayesian formulation of the problem here. Then the belief state will be all the intermediate posteriors as you do the sequence of experiments. So then the transition or the update from one belief state to the next will follow Bayes' rule. So here is the formula for the Bayes' rule. So imagine you have done K experiments and then you're just doing the next K+1th experiment. So before you have done the K+1th experiment, you have an initial prior belief with respect to that new experiment. So that's the PDF of theta conditioned on all the previous experiments we have done, multiplied by the likelihood for the new experiment and normalize it by the marginal likelihood or by the evidence, then you get the Bayesian posterior on the left-hand side, which is the updated posterior of theta conditioned now on including the new experiment, the kth experiment as well, or sorry, K+1th experiment as well. And that will be the belief state of XB of K+1. So all the belief state updates are rigorously updated through the Bayesian framework here. So pictorially, you can think as we start with some prior, we do the next experiment, we update it to the next posterior, we do another experiment, we update to the next posterior, so on and so forth. So very naturally, a sequential Bayesian inference framework can help describe this there. Now, an interesting question is, conceptually, we can think these belief states to be posteriors, but in practice, how should we represent them, right? And there could be many different techniques to do that. Maybe one is just discretize the PDF and just keep track of the PDF points, values as they're being updated. Another one is, but that might not be very scalable. Perhaps a particle representation or sample-based representation of the posterior might be better and connects very nicely to sequential Monte Carlo, or perhaps just keep track of the moments. Whatever it may be, we have to think about the computational cost in using that representation, but also how easy it is to do these Bayesian inferences. As you can see, we need to do all these Bayesian inferences en route to do the sequential design there. Okay, now if we want to find good or optimal experiments, we better define some rewards or utilities for it. So first we'll have a stage reward or stage utility, and as an example, it could just be the minus cost of doing this particular case experiment. But we also want to have some meaningful indicator that tells us the value, the information we have gained from all the experiments that we have done. One popular approach following the pioneer Li in all the information-based type of experimental design is to use the information gain. So that's the Kullback-Leibler divergence between the final posterior to the initial prior, and we'll have expectations around this. So this will be the expected information gain, which is also equal to the overall mutual information there. So some attributes and possible challenges of our particular problem setup here is that first we have a model-based problem. So we don't have transition probabilities explicitly, but rather we can sample the transition by using the model that we have to sample the different possible measurements that we might get. So I need to keep that in mind. We have a planning problem, so we're looking for the optimal design policy. It's a finite horizon problem, arguably making this problem harder because now we have to keep track of all the individual policy functions for each of the experiments. We're working with infinite state space, so continuous design variables, continuous observation spaces, continuous theta, the parameter we're interested in. So the belief state are general non-Gaussian posteriors for continuous random variables. So the practical challenge is how do we represent that on a computer? Computationally can be interesting and difficult. Transitions needs Bayesian inferences, and that can be very expensive. So each Bayesian inference itself is already typically very challenging. Now we need to simulate many possible Bayesian inferences under different scenarios. That is just another order of magnitude of expense, let's say. Rewards are information-theoretic metrics, so even how to estimate the KL divergence is an interesting problem in itself. And the policy is mapping from functions to Rn because it's mapping from X. And remember, X is the posterior of a continuous random variable. So how do we represent the policy? That can also be difficult there. So I think this is all making the problem very exciting and rich, and we're going to try to see how we initially take some steps to address some of these issues. Okay, so let's make the problem statement. What is the problem we're trying to solve here? So the problem is that maybe we'll start from the second half, is the sequential optimal experimental design problem, we're calling it, or sOED in short, is that we want to find the optimal policy pi star that maximizes this objective function, or this big U that is a functional of pi here, subject to any of the system dynamics that we have, and also any any design constraints that we may have there. And what is this U of pi? Well, that's the typical expected total reward that we have. And so that's the sum of all the stage rewards or the immediate rewards plus the terminal reward in expectation over all the different possible measurements we would get from the experiments, conditioned on following the policy pi and a starting prior belief state that we have there. So that's the problem statement for our sOED problem. How do we go about tackling it? So some of the past efforts is that we can approach this in a dynamic programming way and write down the Bellman equations for this problem. So these are V functions, the value functions or state value functions or value to go functions, which are nestedly defined. So it's the max of the EXP of the reward for the current experiment plus the same value function, but now at the next stage until the end there, right? So, so this is the typical Bellman equations, and one strategy is to try to maybe solve this problem. Is to use value function approximation. So you can use some functional approximator to represent the value function here, so V hat, and then maybe build these V hat approximations in a backward induction manner. So you start from the terminal reward, which we know, and once you have an approximation, and then you can plug it in here to take the step forward to n-1 and do an approximation, functional approximation, and then n-1, you go to n-2, so on and so forth until you get to k equal to 0. So the classical backward induction approach there, and that's what we tested out in an effort a few years ago, and has some good results, but it was very expensive. Backward induction, very expensive. So what we're going to do in this work is something different, and forget about approximating the V functions. Let's just directly look at the policy functions and parameterize the policy. So again, here we're back to the problem statement, the same as before, but wherever you see pi or mu, we're going to parameterize it. So pi is replaced by W, or parameterized by W here. Mu is parameterized by WK here. So, so W is the policy parameter, and W you can think as the weight parameters, let's say, of a neural network parameterization of the policy there. So in that case, we have turned in searching in a function space of policies into a finite dimensional vector space. So the W here, right? So that would be a finite dimensional parameterization of all the policies here. And we're just going to look for the optimal policy weights or parameters, W star there. And furthermore, if we can get the gradient information of U with respect to W, then we can take advantage of gradient-based optimization algorithms like gradient descent or stochastic gradient descent even. So things can help us accelerate towards the optimal policy parameters W star faster. So that's the idea here. Okay, so so skipping a lot of the derivations, but one of the key theorems that we derive is the policy gradient expression for this finite dimensional with this Bayesian update, Bayesian belief state for continuous random variable setting there. And it's equal to this big thing. And most notably is that there are two components to it. One is that there's the gradient of the policy function with respect to the W. And there's another term that's the gradient of the Q function, which is the action value function, with respect to one of its input arguments. So the action or the design here. So these are two things that we need to be able to at least estimate numerically in order to propose a computational algorithm. So that's what we plan to do. So first, this whole policy gradient, we can use a Monte Carlo estimation of it. So the expectation, you can think as replaced by a Monte Carlo estimator. So that looks like this. Pretty much everything else stays the same here. But what we need to further do right? So is that let's look at these gradient terms. The gradient with respect to the policy, we can do that because we have already parameterized our policy. So if we're using a neural network, we can use backpropagation to get the gradient information with respect to its parameters very efficiently. So that's good. But what about the second term? We need to take the gradient with respect to Q, of Q with respect to one of its arguments. To do that, then we should also try to, or we need to parameterize, or that suggests that we should parameterize Q as well. And if it's in a nice parameterized form, then we can also take its gradient very easily there. So that motivates the parameterization of Q function as well. And that makes it into an actor-critic formulations. So we're parameterizing and approximating both the actor, the policy, and the critic, in this case, the Q function, the action value function here. And the action value, the Q values can be estimated through simulations, Monte Carlo simulations, since we have a model, so we can simulate different trajectories or episodes. And from following, let's say, a particular policy pi here, and from that simulation, we can estimate all the value to go, the cost, the reward function of the tail portions depending on what experiment we are. And from those estimates, Monte Carlo estimates, then we can do a regression to approximate the Q function. And let's say the Q function is also parameterized by the parameter nu here. So both the mu or the pi and the Q are parameterized in the end there. Okay, now another important question is how do we actually parameterize the policy and the Q function there? Like what form do we want to use? So we're going to use neural networks here, kind of inspired by the deep Q network work, the works of the deep Q network and DDPG. So we're going to use neural network to represent it. Further, so let's look at the policy neural network, for example. So the policy, we're using a deterministic policies in this framework right now. So, so the policy maps from a state to an action or a design D. So what is that state representation? The problem that we kind of hinted on earlier. So these states are conceptually Bayesian posteriors for random variables, continuous random variables. How do we put that as an input to the neural network? So some options could be, let's just input the moments, for instance, or maybe some summary statistics of these posteriors if they are easy to compute there. So for now, we're going to take another kind of avoid the problem of how to represent the posterior state, but rather just take a more of a kind of non-parametric form and just say, let's just keep all the D's and Y's. So all the designs and the observations from the experiments that have completed so far. So literally all the things that are being conditioned in the posterior. So those are by definition a sufficient statistics without any approximation error to the posterior. But the problem is, as you do more experiment, this input vector of all the designs and measurements would grow, right? The more experiments, so the dimension would grow. But luckily, since we're working with finite horizon, finite experiments, they're capped. There's some maximum that it cannot exceed, since it's a finite number of experiments we're dealing with here. So what we're going to do is we're going to construct the neural network with this maximum input dimension. And as a starting point is that any of the experiments that haven't been done yet, we would pad it with 0. And as they are being completed, then the actual numbers can go in there. So in that way, we are representing the belief state, the posterior, to mapping it to the design action at the end there. And any physical state, we can also tack it on at the end to augment this input space. Okay, so to summarize the overall algorithm, so this would be a deterministic policy gradient for sOED, and if we're using deep neural network representations, so that would be a deep deterministic policy gradient, but for tackling sOED here. So we would first initialize the policy and the value function parameterization with some W naught and V naught or nu naught, and then enter a loop to do these updates. And we would first sample n episodes, so this Monte Carlo sampling of trajectories following the current policy pi wi, and therefore we get all the sequence of states and designs along the way. And we can also compute the posteriors if we want along the way. And then we can estimate and update the Q functions after as we get all the states and action and also the rewards. Then we can update the Q function, let's say by regression. And now we have the Q and the policy pi's, so we can then just put it into the formula to estimate the policy gradient and take a gradient ascent step. And we can just iterate this process there. So overall, the structure, the steps are doesn't seem complicated, but the computations can get quite intensive there. So let's look at some of the results. Let me just take a look at time. Okay, results. So the first thing we did is a benchmark problem, just as a sanity check to make sure that everything is working in as expected for something we know how should work. So we do that on a linear Gaussian or linear normal benchmark problem. And we have a conjugate system if we have Gaussian priors and the linear model, so the posteriors are analytically Gaussian as well. So only in this particular case, we have an exact solution. And here we plot the expected utility and over the design space for two experiments, D's naught and D1, and there's an optimal front of designs. The contour is the exact solution. And we can see that if we use dynamic programming, previous approaches, all the simulation points or the computations would gather on one part of this the optimal front. So that's good. And for using policy gradient, they gather at a different part of the optimal front. So that's good too. And the average, the mean total reward, 0.786, are all very close to the theoretical optimal, 0.7833 in this case here. So that's a good sanity check that it's doing things right and finding an optimal policy. But what's interesting to note is that the time it took to do the computations, if we do the adaptive dynamic programming, the training time, it was, let's say 4,000 seconds, whatever that is, maybe, just over an hour. And lots of model evaluations and the testing time also very high. Policy gradients were about an order magnitude lower in the training time, and the testing time is much lower as well. The reason why the ADP is so much higher is because it's approximating the value function, so the policy is not represented explicitly. So if every time we need to evaluate a policy, we need to do an optimization problem over the value function. So that's why the testing time, you're doing optimization online, right? So that can be very expensive. So it's not surprising that the policy gradient can be much faster there. So here's a more complicated type of example. So we're going to look at a diffusion problem, contaminant diffusion in a two-dimensional domain. So this is the diffusion PDE with a source term. So there's some contaminant being leaked or generated from the source. The source has a Gaussian-like profile, and we assume that we don't know where the source center is, and we're interested in inferring that. So we want to infer the source location, where we can take measurements of the concentration of the contaminant at different locations. So we want to design for where to place the sensor. So to begin with, we're going to just build some intuition from a one sensor design. So if you ask me in the square domain, you can only place one sensor, where do you put it? My first instinct is to put it in the middle of the square domain, and that's precisely the worst place to put it in this case. The best places are at the corners in this case, right? So I think very naturally we may have this notion of we want to fill the space filling, so put it in the middle. But in terms of model-based simulation, the design, we can actually see this, in this case, that's actually the opposite. We want to put at the corners there. So for the one sensor design to build the intuition is that the corners are better. So I'm gonna skip some of these details and now go to the two sensor design. And so this is now sequential, multiple sensors. And in this case, to really show the difference or the potential benefit of, I think I hear a siren, of sequential OED design, we're going to make it such that the source is off initially, so time is going, but only after some time it starts going on, right? So to really show there is a benefit to look ahead into what might happen in the future when you design all these experiments there. So the source is only activated after some time. We're going to do two experiments. To illustrate this, the first experiment is before the source is on. So that's going to be a useless experiment. We know that, right? And the second one is going to be after the source is on there. The sensor is initially in the middle. So you imagine we have a truck, we can drive the sensor around. So initially it's in the middle of the domain. And the design constraint is that there's some range we can go to around us there. The reward, there's some penalty on the movement and with the expected information gain at the end there. Okay, so let's compare sOED to, let's say, a greedy or myopic design here. So we start from time zero, nothing's happening yet. We have a belief state, that's a uniform prior of where the sensor is in the two-dimensional space there. Same uniform prior for the greedy design. And on the left here, the purple block is the physical domain. So our starting vehicle in the middle. And in this case, as illustration, let's say the true source location is over here at the purple domain here. Okay, so in the first experiment, right, let's see what's happening here. For greedy, let's start with greedy. The vehicle doesn't move because it's smart. It knows that the source is not on yet, right? This is the first useless experiment that we have. So the source is not on. We shouldn't go anywhere. There's no point to spend our fuel, our gas for the car to go somewhere and then take a measurement where there is no source. It's going to be no information at all. So the posterior is the same as the prior, right? It's the same here. I think there's some message chiming notification in the background there. So for sOED, we can see that it already makes a move towards one of the corners. Remember, the corners are good. That's the intuition we built here, right? Corners are good. So, but it didn't get any useful measurement because the source is not on yet. And indeed, the cumulative reward thus far is negative. We spent some effort to move somewhere without gaining any information. So it sounds like it's done a bad choice. But if we go to the second experiment, you can see now, aha, the source is on now, and the vehicle can get to much closer to one of these good corner locations now, right? Whereas the greedy design, it knows, oh, the source is on, let's start going, but it can't go that far. It can only get to, let's say, midway to the corner here. So both of these locations, we're now getting an actual informative type of measurement here. It's telling us something, but it's more informative in the sOED case. We can see the posterior. After the two measurements, the posterior is narrow, qualitatively speaking, is narrower compared to the posterior from the greedy design. And you can, that's also reflected by the total reward now, including the terminal reward, the KL divergence. So it's higher, 0.793 to the greedy 0.732. Now, this is only for the case where the purple dot is here, and for this particular realization of the noisy measurement. Overall, we need to take the expectation over all possible source locations in accordance to our belief states or prior and posteriors, and also overall the likelihood, the possible measurement error there, to arrive at the overall expected total utility or total reward there. So we do the simulation. 10 to the 5 times under all those different samples. And we can get a histogram of all the total rewards. And we can see the mean reward for sOED 0.614 is indeed higher than greedy in this case. So that's good that sOED is doing what we think is doing and bringing the benefit that can be understood from a intuition, from a physical point of view of the diffusion process there. Then further on, we have also included convection, right? Because we want to increase the complexity of the problem where things now get really less and less intuitive. And in this case, we have diffusion, and then we have wind picking up to push this plume towards the upper right direction here. Without going into the details, again, we have simulation results to show the mean total reward for sOED is, again, higher than the greedy there. And all of these are not surprising because mathematically we can show the optimality of the sOED formulation there. Okay, so I think I'm going to end with some concluding summary remarks here. So we presented a general Bayesian OED framework for multiple experiments, enabled the policy gradient for the sequential optimal experimental design, demonstrated the advantages of sOED in several source inversion applications. There are lots of exciting future directions to explore. One is how do we efficiently represent the state and to do approximate Bayesian inference ideally fast. Another interesting area is to perform inverse reinforcement learning to extract human preferences from the experimenters because they may not only be interested in expecting information gain. There could be other things that are of interest. So how can we maybe try to learn that from their experimental decision? That's something I'm very interested in. And of course, scale to higher dimensions. That's also, that I would say is a current limitation of our framework, that we can only handle maybe 5-dimensional parameter space right now. Which just quickly acknowledge our sponsors from DARPA and the Department of Energy. And we said, thank you all very much. I'm happy to take questions or the discussion.
Thank you, Xun, for the very interesting talk. Shikai, can you please start to lead the discussion? Maybe you can start from leading the for the question in the chat window. Start from yours.
My question. Okay, so I asked one question. So when I say the network architecture, it seems to be very complex. My first question is that can we try sequence modeling to get a history embedding so that to simplify the network architecture?
A very interesting
It's very easy to handle even for infinite horizon problems.
Okay. I think that would be great. It's something we have not quite explored yet, but I think that would be very, very helpful to do the history embedding because that's exactly what we need, right? That's all the things that we condition on. Yes, absolutely. That's an excellent suggestion. Thank you. Yeah.
Okay. Renza also have 2 questions. The first one is, do we expect to benefit from decomposing the terminal reward into one reward per round based on the area of information gain? Yeah, I guess you have the proof again.
Yeah, I did not show it here, but that's an excellent question. So let's go to where did we? Right here. So right now, the formulation we have is there is nothing about information in the stage or the immediate rewards. Everything is kind of clumped together to an overall information gain or KL divergence from the final posterior to the very initial prior, right? The overall information gain there. So alternatively, that's an excellent point there, is that maybe we can look at incremental information gain or incremental KL divergence, right? So not just this one big thing at the end, but we can here, or rather after that, we can add to KL divergence from xb comma k plus 1 to xbk, or maybe k to k minus 1, depending on the notation. I have to think about it. But in incremental KL divergence, right? So we can do that. and sum them up. And in fact, they are equivalent to each other. And we also do have a proof in the manuscript there, but the intuition behind why they're equivalent is because there's all the expectation outside of it. So there's a nested expectation outside as well. So the expected the expected sum of the incremental KL divergences is actually equal to the expected total KL divergence. So they're actually equal in the utility or the total utility overall. Now that being said, there could be very interesting considerations from a numerical point of view, because all these Q functions or these value functions and policies that we want to represent and approximate, right? Maybe that the fact that we divide it up into multiple incrementals can be numerically more friendly to approximate. And I think the intuition just overall from reinforcement learning, right? If you have all the reward just at the end, you get 0, 1, but nothing you don't know in between, that can be typically a lot more difficult than if you can spread it out to guide the learning process there. So there could be interesting thought in terms of especially from a computational point of view. Yeah.
Okay. The second question is about have you compared your method with some of the variational Bayes methods? I guess that's brings the second question.
Variational Bayes method.
Yeah.
Oh, sorry. Go ahead. Go ahead, Dr. Liu.
Oh, and that's all. I mean.
Oh, that's all. Okay. Yeah.
What's the comparison with between your method and the variational Bayes method? Yeah.
Okay. So we have not done any work here yet on variational Bayes. It's something on our list because it's very interesting to do the variational Bayes inside the sequential learning process or sequential design process there, so that maybe we can have an efficient approximate representation of all the posteriors rather than trying to get the full posteriors, but the approximation can be justified in an optimal sense from a variational point of view there. So I think that's very interesting, but we haven't done that yet. We're doing some preliminary investigations to try to bring in variational inference into this, but the short answer is we have not done that. Yeah. Is
okay.
And if you're aware of relevant work that people have already done, let's say in investigating variational inference from a sequential experimental design, I would love to, please do suggest to me. I would love to take a look.
Renza, do you have any literature?
Oh yeah, I read some. There are some recent papers, and I can maybe send offline. Yeah.
Yes, please. Thank you very much. Thank you.
Okay. Also, Peter, I have one question. So his question is that can we use some kind of no-dimensional summary of the posterior as the state?
That's my hope. I would love to have that. So I think that's one of the challenges of wherever that. Yeah, like how do we summarize this posterior? And I think maybe one approach is to use some sort of variational approximation. So like if we were using Gaussian approximations to all the posteriors here, then we can just keep track of the the mean and the covariance matrix as we go along there. But there would be some kind of approximation error being accumulated along the way as we do the sequential designs there. So I think that's what I would like, and I think definitely one can just do that, right? I can just take the mean and covariance and say I'm going to use a Gaussian approximation, but I think to understand how much let's say approximation error is being involved here is something I think is very interesting and maybe need to be understood more there. But I think that's an open area, right? How do we represent the posterior so that it's rich enough? And also we can do Bayesian inference. So we don't want to do do some too much of a summarization that it's not enough or not sufficient to do the subsequent Bayesian inferences, then that might introduce more errors there as well. Yeah.
Okay. I guess Peter has another question. Question is that can we restrict our policy choices? So for all the mu case, to constrict all the mu case to be the same.
Oh, yeah, we can do that. So we could just instead of n mu case, we can restrict it to be the same. That's okay. I guess. Okay, I think I'm thinking two possible variants there. The first is that maybe from an implementation point of view, like instead of having, let's say, n neural networks, one for each of the mu k, we can combine them together into just one big neural network, right? But one of the entries, one of the inputs to the neural network is k, like which and that's what we have done here, right? So we actually just have one policy neural network that like all the mu's are in there, mu1, mu2, mu3, but one of the inputs is the stage index k, but we use a one-hot encoding to it. So in that sense, from an implementation point of view, we don't need to actually build n different mu case. We actually have one, but it's essentially mu is now a function of x x comma k, right? K is one of the inputs there. So augmented, I'll combine them together. So that's maybe one variant of like having one mu. The other one is maybe from more upstream, from a formulation point of view, is that we just, even before talking about any implementation on numerics, just from a formulation point of view, if we want to restrict all the mu's to be the same there. And we can definitely apply that restriction, right? We just say, whatever experiment you're at, we only have one mu that we're going to use there, and they're all going to be the same policy, or we're restricting them to be the same policy. I think then in that case, it would certainly be easier to handle, easier problem to handle from a computational point of view. But I think that could also introduce approximation errors because we are limiting away some of the freedom to have their individual policies for each of the experiments there. And how much of a difference is that making, right? It's an interesting question. I would think it's definitely problem dependent. If it's a problem where very naturally all the policies, all the optimal policies are very similar anyways, right? Then if we have made that restriction, then I think we wouldn't have introduced much error. But if they're very different type of policies, and in fact, the policy, the type of experiments can be completely different, right? So in one, maybe the design space is just a different dimension than the other experiments. So I think in those cases, we may have to keep track of the different policies just because they're different spaces even. So I think that's very interesting, and there could be lots of investigation to see what's the trade-off between restricting them to be the same versus any errors that we're bringing there. So yeah, thank you for that thought.
Yeah, I also think that it's valuable to compare with that.
Yeah.
Okay, any other questions? I guess that's all the questions. Can I share the screen? So I have other two questions. Actually, so actually for the, can everyone see the screen?
Yeah.
How to, yeah. So thanks for the nice talk, Dr. Huan. So for the discussion, I'll first ask several questions, and then I'll talk about some of my personal experience in tech industries about design of the experiments. So before the questions, I'll probably I need to talk a little bit about my personal understanding of this talk. So for the design of experiments, in my eyes, it's just a data collection process, which is efficient for the downstreaming tasks. And the downstream tasks are most of the time just policy optimization or policy evaluation. So how to evaluate, how to optimize a policy, or how to evaluate a policy in a very easy way. But in Dr. Huan's talk, it's about how to learn a policy to conduct efficient exploration so that we can estimate the parameter that controls the system dynamics. So there is one prerequisite about Dr. Huan's method is that we have to get a simulator, which is the correct model with unknown parameters. And the problem is how do we estimate the parameters, collect data? How do we collect data in an efficient way to estimate the parameters? And the reward is defined as the KL divergence between the prior and the posterior of the parameter. And then they apply a actor-critic method to solve this problem. So actually, my first question is, if there's no true model, how do we define the reward, and how can we change or do a simple modification of this method to solve this problem?
Dr. Luo, did you want to us to discuss, or wait until you finish?
No. Okay. I thought maybe you can comment first, and then I can do my second question. So
yeah, I think this is an excellent point. And right now, as you have seen that we assume the model to be in the right form, but just the parameter is unknown, and that can be a big assumption. In real life, all models are wrong, right? So what would be the effect of assuming that is the right model there? I think there's definitely an interesting opportunity to incorporate the effects of modeling error or model form error. So there's a lot of work, at least from the statistical research, like model discrepancy, model inadequacy. I had one paper, a pioneering paper from Kennedy O'Hagan that I always cite about how to handle how to try to handle modeling error. I think in that paper, the 2001 Kennedy O'Hagan paper is add another additive or maybe a multiplicative term, perhaps using Gaussian processes to represent it there. So I think there's a lot of advances in the model discrepancy, model error research that can be used to make this framework more robust as well. And that's something we haven't done yet. And I think that we should do. So whether it's also having these model error terms that we're also learning maybe together with these thetas, or maybe we have multiple models, multiple candidate models, and we can do an expectation over this distribution of possible models as well. So I'm also thinking perhaps approaches from model Bayesian model selection or Bayesian model averaging could be useful. We can try to estimate the base factors or the model evidence from them, right? So we can have a weighted average of a set of models that can potentially be more robust as well. But overall, I think this is always a very important problem and hard problem.
Yes, so if we increase the number of models, the number of parameters also increased.
Yeah, so the computation is going to be right.
Yeah, that's it's very hard to apply in real applications.
Yeah, but I think maybe that's the goal we should aim, right? Because as we develop better algorithms, better computers, maybe we'll get closer to that reality. Yeah.
Okay. So the second question is that actually I've been in industry for several years. The key criteria that I choose one method is about the stability of this method, even no matter how it's offline mode or it's online in production. So my second question is about what's the stability of this method over all the parameter choices or even the network architectures and any rate and others.
Another wonderful question. So we have not reported a very systematic, let's say, sweep of all these different hyperparameters and all of these. So I cannot give you a definitive answer. And again, that is an excellent suggestion. Maybe we should also do more investigations there as well. But right now is mostly built based on trying out some of these different combinations that we have based on experience found a good setup there. The one thing that we did note, I think I can comment on, is that compared to the dynamic programming setup that we had previously, it seems like the stability is a little bit less stable with the reinforcement, with the policy gradient there. We're not sure exactly why that is the case, but that's something we have observed. So in terms of converging to optimal policy, etc., it seems like the dynamic programming is a bit more stable, a bit more robust in overall under all these computations there. Now, but the speed is so much faster for the policy gradient there. So yeah, so I think the stability is something that maybe we should also investigate further, more systematically. Yeah.
Yeah, that's very important for industrial application, I guess.
Agreed. So, yeah.
Okay. Next, I'll share a little bit about industrial practice. So I've done in Didi and Tencent and ByteDance. Actually, we only talk about classical design that Dr. Huan had talked about. It's a little bit different with Dr. Huan's talk. So the reason is that we don't have a model because the environment that we're facing are too complex to model, or it's too complex to model with only a finite number of parameters. So to conduct the first experiment, most of the time we just do a random exploration based on our prior expert knowledge. So the situation is that we want to intervene our users to make sure that to increase the frequency of those users to use our app, like Didi or TikTok, other apps. So we have several actions to apply on those users. For each given user, we have a prior knowledge what kind of actions that is best for this user. So we will apply this action to those kind of users with high probability, and for the other actions will give less probability. So it's not a completely randomized exploration, but it seems like to be an epsilon greedy exploration based on expert knowledge. So to minimize the the cost of the experiment. So this is also what Dr. Huan has talked about, as the experiment is very, very expensive. So we try to incorporate all our prior knowledge to minimize the cost of the experiment. But it's a greedy version. Then for the next experiment, after we conduct the first experiment, we have a lot of data. So then most of the time we'll use this data to do color inverse, to do uplift modeling. For each user, we'll estimate what's the expected outcome for this user at any given action, and then we will do a greedy design for this kind of user. So we compute for each user, we compute the expected outcome at each action. So we get let's say we have 3 actions, we get Q1, Q2, Q3, and then we'll choose the max Q, the action that gives the maximal Q value for this user. And then it's just a greedy design that Dr. Huan has talked about. And we'll still choose a small amount of groups, a small amount of users, and then to do the soft Q randomization as well, so that we can continue optimize our experiments. But this kind of optimization are always one step. So there is a problem that Dr. Huan has talked about, is that we do not look ahead. But to solve this problem, we also consider a score that is related to the next state retention. What do we mean that? So we apply one action to the user. Let's say one user, we apply one action to this user, and we want to know whether this user will come tomorrow or not. So it's a score related to the next state retention, and we'll also incorporate the score to our decision process to solve the problem that we do not look ahead. So we also tried RL, but the reasons why we do not use RL, or why we do not see too much real application of RL, is that the immediate reward almost contains most of the contribution that the intervention gives us. And one intervention on one user cannot change their state very rapidly. So the state change is very, very slow. It's not like video games. We can collect an episode with thousands of steps. But for users, one step means one day. We can't apply actions on the same user for thousands of days. That means several years. So that's also almost impossible. And another consideration is that it's about engineering shift. So to apply RL in production, we have to change all the engineering infrastructure. And how do we collect the online data? How do we do model streaming update? Not of them. So it's very difficult. So that's the reason why we almost always do not choose RL. So we're still trying it. We don't see too much gain. I guess the main reason is that the immediate reward contains almost all the contribution of each action. So yeah, that's all my discussion. So any questions, I'll welcome. Yeah.
That was very interesting to have a perspective from actual usage of all these methods there. I just had another thought to echo your comment there, that the look ahead. So that you have a score there, right, for the next day, which I guess is kind of similar to having some form of model to try to estimate what might be the retention next day. Would that be a right way to think about it?
Yes, yes, it's a model.
Yeah, okay.
Yes.
I see. Cool. Great. Yeah. Now I was also thinking this, like looking ahead even longer, right? Is that I feel a very interesting question is how much benefit can that bring? Because maybe in theory, it can always bring more benefit, but it might just not be worth it in practice, which I think is kind of maybe what you're hinting in this case here, right? The immediate reward tells us almost everything about
everything.
Right. So and I've been thinking a lot about like how can we know, because in some problems maybe it does bring a lot of benefit from looking very long ahead, but others maybe not so. But if there's some way to estimate the potential benefit of looking ahead, right, that would be in a cheap way, in an inexpensive way, that'll be really useful in terms of just choosing, should we use greedy design that's already really good, or maybe do we really need to try to do a longer horizon full RL type of approach there? So so that reminded me of that thought, and I don't know the answer how to do that, but that's very interesting.
but we're still trying there.
Yeah.
I was trying. Every time we face a new problem, we try to try the greedy design first, and then try to solve the look ahead problem with a very simple fix, and then try RL. But we saw some kind of we have seen some kind of improvement for the second step. I mean, look ahead. But for RL, we don't see too much gain.
Right.
I've been in 3 companies, but even for 3 companies, I don't see too much real application of RL. So I mean, real RL. It's
right.
It's very complex. I mean,
Agreed. Thank you so much.
thank you, Dr. Huan. So.
Well, thank you, Xun and Shikai, for the very interesting discussion. And I think there are a lot more we can discuss, but let's do it offline. It's time for us to conclude for this talk. So I would like to also thank all the audience to be here today. We will see you next time.
Okay, see you.
Thank you, Ray. Thank you, everyone. Thank you, Dr. Luo. Thank you. Bye-bye.
Bye.
Bye.